Okay, now that we have everything working, number one here, we add those together, 48.3 inches plus 7.92 inches. We're going to get 56.22. Number two here, we're going to multiply 6.37 times 5.3, giving us 33.761. That's going to be inches squared. Now again, multiplying and dividing, we are worried about accuracy. That is the number of significant digits. So this has 3 significant digits, where the 5.3 is 2 significant digits. So our answer has to be rounded to the lesser of those, which is the 2 significant digits. So from the beginning, we go 1, 2, and we have to round it there. That's going to round up to 34 square inches. Number 3, we're asked to divide. 25.2 divided by 3.7. We're going to get a continuing decimal here. We get 6.81081. Continuing on. Now we're dividing, just like multiplication, we're looking at the number of significant digits. Looking at accuracy, this has 3 significant digits. This has 2 significant digits. We're going to round to 2 significant digits. So that'll be 6.8, and the units there are pounds per square inch. Finally, number 4, subtracting. 568 inches minus 28.4 inches is 539.6 inches. When we add or subtract, we're worried about precision. Well, this is precise only to the nearest 1 inch. This is precise to the 1/10 of an inch. So the lesser precision is the 1 inch. So this is rounded to the nearest whole inch. Well, that 6 tells me to round up. That has to round up to 540 inches. However, I cannot leave it expressed like that because this is rounded to the nearest single inch. Even though that digit ended up being a 0, that has to be indicated as a significant digit. So we indicate it by putting a little line above it saying that 0 is significant. It just happened to be closest to 540. Did anybody get all 4 of those correct? Okay. A couple of you did. That's good. I realize this is one of those topics that might seem like just a totally foreign language to you, and I get it. This is engineering world, design world here. Some of you hopefully will move up into that world at some point in your career. If nothing else, many of you will work with designers and architects, and you'll need to be able to read their calculations and understand at the very least why they round things the way they do. Like, to me, the one that's always this one's always kind of surprising because both of these go to the 100th and the 10th, but we have to round to the nearest whole square inch because of those significant digits. It doesn't seem correct, but it is. Well, today we want to continue on a similar topic, but slightly different. We want to talk about errors and sources of errors. Of course, one of the biggest sources of errors is human error. This means the person doing the measurement or whatever just plain screws up. This is one that's really hard to account for and to quantify because it's really tough to decide, when did the person screw up? How much did they screw up? What is that error? This is something that's usually caught down the line in a quality control process, but it's hard to quantify at the time it's occurring. There are Process errors. Process errors are part of the process. When you guys go to drill a hole in a piece of wood, no matter how precisely you place that piece of wood, the tip of that drill hits exactly the point you want it to start drilling into. The tendency is for the tip of that drill, when it hits the wood, it's spinning, it's going to deflect slightly to one direction before it starts to penetrate the wood. It's just part of life. We can't stop it. It's part of the process. The same happens when you're cutting. You might have a jig that you slide the board up against on your miter saw, your cutoff saw. The blade comes down again. That blade, when it hits the wood, might deflect slightly to one side or the other before it starts to cut through the wood. You cannot avoid those errors. They are part of the process. You can design a better process, buy more expensive equipment to try to minimize those errors, but they're going to be there. Then we have measurement errors. These are errors, again, kind of part of the process. They're part of the device that we use for measuring. We can control them by buying a more precise measuring device, but it's something we have to balance out. Generally, a more precise measuring device takes longer to use and to read, so we have to balance that time for precision there. But we're going to be looking at mostly errors. Measurement errors get broken into a couple of different types. Type 1, first type is what we call an absolute error. Now, an absolute error can be thought of a couple of different ways. It is the difference between a desired value and an actual value. Or in a measurement error, that's kind of the process error side of it. In a measurement error, it's the difference between the measured value and an actual value. Now, I list them in this order here, but it really doesn't matter. It's just whichever one's larger minus whichever one's smaller. We don't care what direction it is in, whether it's positive or negative. We don't deal with that. It's just how far it is away from that actual value. So, for example, let's say we have an object that is actually has an actual length of 2 5/16 inches. And we measure it and get a measured length of 2 1/4 inches. This is going to give us an absolute error. Two 5/16 minus 2 1/4, or 1/16 of an inch of error. Now, a 1/16 of an inch seems like a pretty small error. Doesn't seem like anything to get too excited about. But it depends on what we're doing and what we're using it for. Also, it compares back to the size of the object we're starting with. So more useful in most cases is something called a relative error. In a relative error, we are comparing it back to the size of what it is we are measuring. So for this object here, for any object, the relative error is the absolute error divided by the actual value. So for this particular object, our absolute error is a 1/16 of an inch. Our actual value is 2 5/16. So if I divide that out, got to be a little creative on my calculators to enter those. I get 0.027027. Now that seems like a pretty small error. Some textbooks treat this next one as a different error. Other textbooks treat it as just a different way of expressing a relative error. And really that's what it is. It's a different way of expressing a relative error. It is a percent error. So a percent error is nothing more than a relative error that has been converted to a percent. So for this one up here, we move the decimal point over 2 spots, or we make it out of 100, either way you want to think about it. That becomes 2.703%. 2.7027% if you want. The 0.027 as a relative error seems small, but we listed as 2.7%. That's a little big. That's probably more than what we want to allow for an error in most cases. Now, realistically, we don't usually know what the actual value is. Because we don't know the actual value, we can't find an absolute error. We can't take our measured value minus our absolute value. So what we do in most cases is instead of an absolute error, we use the error in the measuring device. So what does that mean? Well, that means if I have a measurement listed as 2.3 inches, that is implying a degree of precision of 0.1 inch, which is implying a built-in error in that measurement of half of that plus or minus 0.05 inches. We would use that as our absolute error. Because we know that whatever the real value is, as long as we did that measurement correctly, that should be within 0.05 of an inch of the real value. Now I'm going to do two examples side by side here. I'm also going to do 47.8 inches. That also has a degree of precision of 0.1. So that should also have an error of plus or minus 0.05 inches. And we'll use that as the absolute error for that measurement as well. So now the relative error for each of these, we don't know the actual value, but we know that whatever the actual value is, as long as we did our measurement correctly again, it should be pretty close to our measured value. So to do our relative error, we're going to take that error of the measurement, the 0.05 inches, and we're going to divide by our measured value, 2.3. 0.05 divided by 2.3 gives us 0.0217. If I convert that to a percent, 2.17% error. Again, that's probably too high. Anything over 1% is starting to get pretty high. Over here, however, we have the 0.05 divided by 47.8, giving us 0.00105 is a relative error. If I turn that into a percent by moving the decimal point, it's 0.105%. About 0.1% of error. Much better. The moral of the story in this example, well, these two examples actually, done side by side, is that the precision of your measuring device needs to match up with the size of the object you're measuring. If you're trying to measure something precisely and it's 47 or 48 inches long, measuring it with something that only goes down to the nearest tenth of an inch is probably okay, because that tenth of an inch is only going to be about a 0.1% error. It's only going to be plus or minus 0.05. But if we're measuring something that's only a couple inches long, if we're trying to measure it precisely, using a measuring device that only goes to the 1/10 of an inch is probably not precise enough, because that error of 0.05 is going to give us more than a 2% error on it. So you need to make sure you're matching whatever you are using to measure, the precision of your measurement, with the size of the object that you're measuring. I'm going to shift gears a little bit yet, looking at reading blueprints. For you guys, this would be more on the furniture side than in the cabinet making side rather than the construction side. We might have something labeled like this. What's that mean? Don't be shy. Well, it means we want it to be 0.820 inches, 820 thousandths of an inch. But we are allowed to be off by up to 5 thousandths of an inch in either direction. This 0.820 is called the desired value. That's what we want it to be. Sometimes it's referred to as an ideal value, because in an ideal world, that's what size you would make it. This is referred to as an allowance. We're allowed to be off by that much on either side. Well, just like our measurements yesterday, this gives us, it implies a range. It implies that we can be anywhere from our desired value minus that allowance, that'd be 0.815 inches, to our desired value plus that allowance.
820.
825, yeah.
No.
So as long as our final result, our final object dimension is within that range, we are within our allowance, or what we call within tolerance. Now, a lot of people refer to this as a tolerance. Technically, what the tolerance is the difference between the minimum and maximum allowable size. So this is a range of 10 thousandths of an inch. This is technically 10 thousandths of an inch tolerance. But you see people refer to them either way. You see people refer to this as a tolerance. Some refer to it as an allowance, and this is what they refer to as a tolerance. Technically, this is the tolerance here. So when somebody refers to something as a tolerance, make sure you know exactly what they are really referring to, because in many cases, they're referring to that allowance. Well, we might have a tolerance that is listed like this. 0.400 inches plus or minus 0.5 inches, or 0.5, not inches, 0.5%. Well, the allowance we were given up here is referred to as an absolute allowance. By 5 thousandths of an inch in either direction, period. This one down here is referred to as a relative allowance. The size of the allowance depends on the size of the original desired value. So to find the actual size of that allowance, it's 0.5%, so 0.5 over 100 equals blank over 0.400 inches. We cross multiply. We get 0.002 is that allowance. So this is really saying this can be 0.400 inches plus or minus 2 thousandths of an inch. That is the absolute. allowance that goes with that relative allowance. These are both what we refer to as bilateral allowances. In other words, we can be off in either direction. We can have something listed like this. What's that mean?
Plus or minus?
Well, it means we can be smaller, but we can't be bigger than our desired value. So this is giving us an implied range again of our desired value minus 10 thousandths, the 240 thousandths, to our desired value plus nothing, plus 0. It says plus 0.000. Now this range here is the exact same range I would get if I had listed this as 0.245 inches plus or minus 5 thousandths. So why would I list it this way instead of this way? Well, what we're trying to describe, remember this first number here, this one and this one, are what we call the desired value. In a perfect world, that's what size we really want this. This is saying we really do want it to be 250 thousandths, but we can't be any bigger. So if the machine you're using to cut this part or whatever, this piece, if it's capable of being within, let's say, 2 thousandths of an inch. If you're doing this one here, you're just going to aim for the middle, the 245 thousandths, and let it be off in either direction. But if this is the way it's listed, you're going to shoot for probably 248 thousandths of an inch, and you're still going to be within. So this is telling whoever is making this, if you can get closer to the 250 than instead of trying to just shoot for the middle. Typically, this is a part that has to work with other parts, and you want it to fit as well as you can. In woods, you guys use interference fits quite a bit, not as often as you used to. This is the old, if you used wooden pegs to hold things together, those were interference fits. The wooden peg was actually smaller than the hole, so when you pounded it in the hole, the fact that it was smaller forced it to stick in that hole. It stayed in. Didn't even need glue to hold it in place. So this might look like this. Let's say you have a wooden peg that's listed as 0.250 inches plus or minus 4 thousandths of an inch, and you're driving it into a hole that's listed as 240 thousandths of an inch plus or minus 4 thousandths again. Well, let's look at the minimum and maximum size of the peg. What is the smallest that peg is allowed to be?
.246.
0.246. Good. What's the largest it's allowed to be? .254. For the hole, what's the smallest that hole is allowed to be?
.236.
0.236. What's the largest it's allowed to be?
.244.
0.244. Good. Now for our interference, the minimum interference is going to be when the peg is small and the hole is large. How much interference do we have there?
0.002.
Yes, we only have 0.02 of an inch of interference there. That's not a lot. It should stay, but it's not going to hold up to a lot of force if there's any pull on it. Our maximum interference is when the peg is large and the hole is small. How much interference do we have there?
.018.
Perfect. 0.018 or 18 thousandths. That's actually quite a bit of interference. We try to drive that peg into that hole. If it's 18 thousandths larger than the hole, it might not go in well, or it might split the wood. So there's a lot of things that could go wrong there. So you can see, even though 4 thousandths of an inch seems like a really tight tolerance, or a tight allowance, I should say, it can be too much depending on the application. I have been cheating you guys out of your homework time, so I wanted to make sure I left time today for you guys to work on homework. This is all out of the big book. Starting on page 272, exercise 7-9, 7 through 17 odds. On page 273, exercise 7-10, also 7 through 17 the odds. And on page 276, exercise 7-11, this is 7 through 15 the odds. I encourage you to do at least a good portion of these problems. As we mentioned yesterday, this is a different way of thinking, probably something you haven't done a lot of before. The significant digits might be something you've seen if you took a chemistry or physics class, but outside of that, it's not a common knowledge concept. So make sure you feel pretty comfortable with this. Now, as I mentioned yesterday, this is not something I expect you guys to walk out of this class being experts with. There will be a quiz on it. There will actually be a quiz tomorrow. It's actually out there. If you do the homework and you feel pretty good about it, you can jump ahead and do the quiz for tomorrow whenever you want to. I won't make you wait till tomorrow to do it. We'll do that quiz, and then we will have, on the next unit test, there will be a few problems on this. I will make sure that before we get there, we'll review this again so that you are ready for it when it hits the test. But on an everyday basis, I'm not going to expect you to continuously do your calculations to significant digits. It's not my purpose here as digit expert. Okay, so with that, we got about 12 minutes left, so I'll give you guys the last 5 minutes to get started on your homework.